First of two video podcasts for Chapter 6 in Field Methods in Hydrology about precipitation, measurement, and sampling. Precipitation is the primary water input driving hydrological processes in most systems. I mean, after all, you need a source of water, and usually that water is going to come from a source of precipitation. It may not always. You might have a control volume where you're just defining it entirely under the ground or on the ground surface where there is just surface fluxes. But really, from an overall hydrological perspective, precipitation is very, very important. And of course, it has wide applications in society for use in meteorological forecasting, long-term climate prediction, and then we use it in hydrology to figure out water availability for all of society's needs, and disturbance regimes, floods, droughts that might be impacting natural systems as well as society. So what I want to do in this chapter is refresh the basic concepts about precipitation that you should have already learned in an Introduction to Hydrology class, and then we're going to move on in the second part to the range of technologies for measuring and sampling precipitation. Well, we have to begin with the beginning of precipitation as it forms in the atmosphere, and that's going to require that the water vapor in the air condenses. So you have to have a low enough temperature for the available moisture in the air for it to become saturated and have condensation. Once that happens, then you have to have some kind of nuclei, like a dust particle, that the condensation can grow on. And then as particles interact with each other, they can coalesce into larger and larger water droplets until they're of sufficient size to fall out of the sky. And that can be a process that leads to just liquid water in the form of rain, or it could be in the form of freezing and ice, snow conditions that are over in the other part of this schematic. But one thing I wanted to illustrate is that even once water is falling out of the sky as rain, it doesn't necessarily make it all the way to the ground. In the dry southwest region of the United States and other parts of the world that are arid, you can have evaporation before it gets to the ground, and that leads to what we call Virga, and I'll show you an example of that. You could even have a case where you have clouds or fog near the ground, and that the interaction of that moisture in the clouds with the ground or biota can lead to what we call fog drip, and I'll show you a photo of that as well. So the main point of this slide is just to remind you that precipitation forms through condensation due to saturation conditions, considering water vapor availability relative to the temperature and saturation conditions, the coalescing on a nuclei, and then the growth and aggregation. Okay, so here's just a couple of slides showing Virga on the left, where you can see clouds and you can see the rain in the distance falling out, but before it hits the ground, it's being evaporated. And on the right, of course, it's hard to take a photo of a process, but you can see the fog that's present in this, really, really moist, temperate rainforest could be, or I don't know. I took this picture as either from Australia or the Olympic Peninsula, so maybe you can look and decide. But anyway, where you have fog moving through the vegetation and causing the adherence of that moisture right onto the plants in the ground. So depending on what kind of studies you're doing, you might need to worry about those formation processes, and equally you have to worry about how water is coming out of the sky, because where you're going to go and sample may depend a lot on the timing and spatial pattern of that precipitation. If you think through the mechanisms of how precipitation occurs before you design your monitoring, then you have a better opportunity to monitor what you want. And I can tell you, I was in another meeting yesterday, and this happens all the time, where people want to go and measure stuff without first articulating the conceptualization for why they're measuring and where they're going to measure and how often they're going to measure. So it's important to understand what this slide shows, which are the four of the main causes of precipitation. And these causes of precipitation have a lot to do with changing the temperature of the air such that you achieve saturated conditions, which then causes the processes on the previous slide. So here are 4 different ways that can happen. If you have warm, moist air right up over cold air, then that will cause, as the warm air rises, it will cool. And as it cools, then you can have the opportunity for precipitation. You could have cold air and warm air just head-on collision, and that can cause a similar rise of the warm air and precipitation. You could have heating of the air throughout the day, which you would think would decrease the chance of precipitation. But as that warm air rises, then it will actually cool as you'll have a change in pressure and temperature, and then that can lead to precipitation. And that leads to convective thunderstorms, which I'll show in more detail on the next slide. And you can also have orographic effects where wind is blowing clouds over a mountain, and that topographically steered increase in altitude of the clouds can cause oversaturation and condensation. So with a thunderstorm, there are 3 phases that take place. There's the warming phase, in which there are primarily updrafts, and we're not going to have precipitation at that point hitting the ground very much, but we're basically rising up. Then you have the mature stage, where now you've had a substantial amount of cooling, but you have a mix of continuing updrafts as well as downdrafts, and a mix of processes that are all taking place. And then you have a dissipating stage, where you're now just precipitating out and finishing with downdrafts, as now it's the cooling is causing the moisture and the air to fall again because it's now cooler. So there's this basically density-driven effects. Density is driven by temperature in this case, and it causes relatively extreme focused condensation in what we call a thunderstorm. Here in California, we do have those kinds of thunderstorms, but we have orographic precipitation. This is the phenomenon in which you have, as I said before, wind pushing clouds up against a mountain range, and that causes the clouds to go up. And when they go up, then they cool, and you can have precipitation. The reason why I want to emphasize this again is because what happens in this case is you get significant amount of precipitation on the windward side, and then a deficiency or lack of precipitation on the lee of the mountain. And you can see that here in California, where the western Sierras have very high precipitation rates and the eastern side has very low precipitation rates. That then causes effects in terms of the distribution and abundance of vegetation, forest fire regimes, or lack thereof, and the mechanisms of erosion of the land. Where you have more precipitation, you're going to end up with gentler slopes and more flow-driven scour. Where you have the lee side, you're going to have more slope-driven processes because you don't have as much water. So to achieve the work that needs to get done to create erosion, you have to have steeper slopes. So that gets into a little bit more advanced idea, but it tells you some of the significance of having orographic precipitation and why you have to be mindful of it when you're designing not only hydrological studies, but studies of Earth surface processes or biota or disturbance regimes in ecology. It's helpful to think about the spatial and temporal patterns of precipitation. So here's a map that shows the U.S. mean annual precipitation. If you wanted to have the data that makes this map, you can go to a website that's called Prism, and it will allow you to download rasters of this kind of data on a mean monthly basis or annual basis or over the long term. So that's something that you can look for if you're interested in. But you can see there is a general east to west variability here in precipitation, where the East Coast is getting relatively high precipitation associated with the warm moisture in the Gulf and the Gulf Stream that's coming and heading out into the Atlantic Ocean. That when that meets together with cold air coming from the north, you can get a lot of precipitation in the east. Meanwhile, the west is relatively arid. The moisture it tends to get is dominated by by convective thunderstorms that come out in the late summertime. And then, of course, the Pacific Northwest having a lot of moisture that's there compared to further to the south. So here, if we zoom in a little bit more from the national scale to the regional scale, you can see in California, here is the average annual precipitation with the high in the northwest, the high at the high elevations in the Sierras, particularly the northern Sierras and the southern Cascades. And then the very dry conditions in the deserts to the southeast, and the north to south gradient that's generally here through the Central Valley, which shows the importance of latitude. Now, if we go from an average annual precipitation to a 7-day rainfall period, in this case looking at Florida, you can see that although there's some patchiness in California for its annual average, you can see that there's significant spatial heterogeneity and variability. And this is the key characteristic of rainfall when you look at an individual event. It's not just a nice even sprinkle across all the different areas that are there, but it is highly heterogeneous, and that makes it very challenging to predict and use as a driver of other hydrological processes when you want to do something like a model testing and calibration field study. If we consider precipitation through time, the most important thing is it's highly intermittent, right? I mean, a lot of the time it's not raining at all. And then when it does rain, you have variable frequency or variable intensity. It can be very high frequency, meaning it can come a lot over a short duration. But then, it may again have long duration where it's not happening. So there's changes are occurring very fast when it is raining, but then there can be long periods with no rain. It's helpful to think about the relative magnitudes of all the different fluxes, so we'll try to do that throughout the quarter. Whenever you consider rainfall, when we say, well, what's the most rainfall that can take place? What matters is how much rainfall can take place within a given duration. So here the x-axis is a duration, and then the y-axis is the intensity, and these are the records associated with these different durations. Notice that the highest rainfall rates in the world over the longest durations are all in Cherrapunji, India. And then there are a mix of places, and there seems to be a threshold line that sort of defines the maximum threshold that's there. But just think about it, so over a 24-hour period, right? So that's one day. What do we have here? We have a high of, 60 to 70 inches of rain. So that's a significant amount of rain. My personal experience high so far was in January 2014. I was in Florida, and we had 18 inches of rain fall on us when we woke up in the morning and came out of the hotel. Our car was flooded up almost to my knees with water because there's nowhere for the water to run off in Florida. Some of the world rainfall extremes, just the highest annual average rainfall, almost 12 meters of rain per year. Most rainy days, 350 rainy days in Hawaii. Highest in 1 year, almost 26.5 meters of rain. And some other numbers here that just help to put it in perspective. So if you do calculations and you're making calculations that are yielding numbers bigger than these, you know something's wrong. And that's an important point of this class that I want you to appreciate is that when you're working in field methods or just as a hydrologist in general, you need to apply common sense checks to see if the numbers you're producing make sense. And being mindful of world records can be very helpful in doing that. Both for minimums and for maximums. The last thing I want to say about concepts is not only considering natural rainfall, but what if you're in a situation where you need to create rainfall for a classical experiment? Here's a photo of a rainfall simulator done by my colleague Mark Rismer, and you can see it's a very nice setup implemented in a natural setting on a hill slope where they're using these needles to distribute a nice even distribution of precipitation onto the test plot. So this rainfall simulator allows you to control the intensity, the frequency, the timing of precipitation, And that allows you to investigate the mechanisms of hydrological processes such as rain splash, surface erosion, infiltration, or what happens with processes of saturation. The downside is it's hard to do a rainfall simulator over a large area. You can't carry one of these of too large of a size or too much water, because water is really heavy to carry around. They can also be affected by winds, and these are usually not things you can just buy off a shelf, but which you have to build yourself, and there's a lot of skills that go into that. Okay, so I'm going to stop here. Those are just the quick basic concepts that I wanted to remind you of before we get into the specifics of the measurement technologies for rainfall.